Hello, welcome. My name is Yishai GALATZER. I'm the director for programming languages in AWS. And there's this guy. I don't know if you know him.
Yep. I'm James GOSLING. Been here before. And so I'm doing the second half of the talk, and Yishai gets the hard part.
Well, he will help me out if I don't know anything, right? Don't go away. So we both work at AWS, and at Amazon, we operate according to this thing called the leadership principles. And one of the important ones, which is fairly new to us, it's called success and scale bring broad responsibility. Let me read out to you a detailed description. You can find the rest online. We are big, we impact the world, and we are far from perfect. We must be humble and thoughtful about even the secondary effects of our actions. Our local communities, the planet, and future generation needs us to be better every day. And what I want to talk about today is how we, the Java team at Amazon, put this to use by modernizing and upgrading our pretty massive JVM installations. So you might want to ask, why do you even have a JDK team at Amazon, right? We have Oracle building Java for us. We can just use it, which is, true. However, at Amazon, we have this thing called, Amazon.com. Christmas is coming. Black Friday is coming. Some of you are gonna go buy some presents. Turns out these days are peak days. We spend a lot of energy, a lot of computers running. They mostly run Java. The same stands for systems like Lambda and S3 and AWS. And all these very large systems need to be more efficient, emit less carbon dioxide to the atmosphere, be more reliable and secure. And this is where we come in. We just can't wait for somebody else to take care of it for us. We have to do that work on behalf of our company. But then you come in, many of you who run on AWS, and use systems like Lambda again, EKS or Kubernetes, ECS, or you might be running Spark jobs on EMR. All of that also needs a Java distribution that's reliable, that's performant, that's secure, that gets patches very quickly and on time. And my team provides that. And last and not least is the rest of you and all of us, the Java community. We at Amazon use Java, which means we need Java to be vibrant and successful, and all of us together are contributing to this community, to OpenJDK, to libraries, or just by using it and providing bugs and feedback and trying things out early, like many of you here do. So thank you for that. I'm going to take a couple of small slides to talk about what are the products we distribute, and then I'm going to go ahead and just focus on what do we do to upgrade. So the main product this team shares with the world is Amazon Corretto. It's a downstream distribution of OpenJDK. We release quarterly security releases. We certify it, and we provide these at no cost to everybody. The long-term releases are for Java 8, 11, 17, and 21 released just a few days ago. There's also the feature release train, and in 2018, we actually launched Corretto right here with 3 binary artifacts. Since then, we've been working hard at listening to our customers and providing more artifacts. Support for Mac, support for Alpine Linux, support for Windows, support for IoT, for ARM64, for ARM32, and so on. And today, we release 122 binary artifacts every quarter. One of the most important things we do is the support for the AWS Graviton 2 and 3 processors. These are ARM-based custom silicon available on many of the AWS services. The 2 really important things about these are, one, they provide about a 40% better price performance compared to equivalent x86 instances, and they use, very importantly, 60% less energy. So when we keep talking about CO2, This is a very good way, if we care about the planet, to make things better. The Corretto team spends a lot of effort in optimizing Java for ARM instances. Again, this is a collaborative process with many other people in the industry, including Red Hat and Oracle and others. But because we have all this experience running systems and processes on Graviton, we're able to contribute improvements over there. Last, to talk about AWS. AWS is huge, right? We run across all these geographies. Every one of these is what we call multiple data centers, right? So every little dot here will show you how many data centers are there in how many places and how it keeps expanding and expanding. If we don't invest in optimizing Java, which runs in all of these places, we're just going to keep building and buying and operating and providing power to so many computers. We just have to do better. And the thing is that our scale, we find a lot of interesting things that haven't been found. And I'll give you a few very detailed examples a little bit later. But I can get a phone call once in a while, and they come in, and somebody says, so we operate this system. It runs on 20,000 computers, hundreds of thousands of computers. And once a day, we have this crash, JVM crash. And there's no bug, and we can't really find out what's going on. And we kind of think it's a cosmic ray, but would you mind taking a look? And we start taking a look. And sometimes it takes a day, sometimes it takes a month, sometimes it takes 6 months. But we never actually found a case where it was a cosmic ray. It was always a bug, either could be in the kernel, could be in the JVM itself. And we always find that this bug was reported maybe 6 years ago, 7 years ago, 10 years ago, last year. And we're able to make these fixes on your behalf. All of you will benefit from it, but if you run 100 a computer system, you might see this problem every few months or once a year. We might see it multiple times a day. And really, this is where we come in. What is our advantage? We have very smart engineers. A lot of you are very smart engineers. Maybe all of you are smart engineers, right? There's nothing really special about what we do, except that we have access to this massive, massive payload of many applications and many computers and many variations. And we really serve you as, I want to call it the giant Java lab running in the cloud. So how do we work together? This is a model that AWS shares with its customer, talking about the security model. On the bottom is all the things that AWS provides the security and responsibility for, and on the top is what the customer does. If you work with AWS, you must have seen this before, but I want to present what we call the performance shared responsibility model. So we, and I say we, I don't just mean the Corretto team, I mean the whole Java community. We own making the JVM, the JDK libraries, the language, be it Java, Kotlin, or any other language running on the JVM. Any libraries you might be using, Log4j or Jackson Databind or whatever you use, or the framework, be it Spring or Jakarta. All of this community together, and we're talking about thousands of engineers, work tirelessly daily to make these things better. Well, and you, the application developer, you pick the system design, you pick which libraries you want to use, which JVM, which distribution, which version, which data structure, which algorithm. That's your side of the business. But together, we're building better performance for our applications. And the main thing I want you to take from this talk is the easiest way for you to gain performance, the easiest way for you to do better for the planet is to upgrade relentlessly. Stay ahead on these versions, and you'll just get benefits. And I'll show you a bunch of examples where this comes from. Now, it's not all that great. There's the good, there's the bad, and then the ugly. And I want to give you examples of all three to help you make up your mind on when you want to move and how fast you want to move and what fits your needs, because every application, every company, and every situation is unique. So let's start with this example. This is a service that Amazon is running. It's one of our monitoring services. I'm going to be careful here with sharing internal data. I'm going to show you graphs and show you information, but I'll be able to share only limited amount of information. So this service, what it does, it runs on almost every machine at Amazon, and it collects basic metrics like CPU metrics or memory metrics and so on, and broadcasts them centrally to a system that collects the data. What we've done with this service is take it from running on Java 8 to running on Java 17. This happened, as you can see in the graph on the bottom, in July this year. And you'll see, if you look carefully, you'll see two colors. The blue color shows the worst machine in the fleet. We're talking here about a fleet of a few tens of thousands of machines. So the top 5% of machines use up to 40% of the system memory, where 95% of the machines only use 21% up to 22.5% on a regular basis. That means that these machines are running at the maximum allowable capacity because we can have a network issue in one of the areas and they need to take extra capacity. And what we always want to do is run the same application on either a smaller machine or on less machines, right? You have these two choices when you're trying to optimize the usage. And it turns out that in the cloud, it's about the same thing. Running on a smaller machine just means you take a smaller slice of a VM. So at the scale of the cloud, you're really doing the same thing by taking either choice. What you see here is after this migration, not only the memory went tremendously down, it became a lot more stable. You can see two spikes around 5 p.m. on July 8, 28, but the situation is a lot better. Overall, we're seeing about a 50% reduction in memory in the worst case, which is mostly what we have to think about. And as a result, we're able to descale the fleet quite significantly, save many millions of dollars, save a lot of CO2 pumped into the atmosphere. Here's another example. This is another monitoring service. This one monitors application performance. So it will take data like your latency or whatever else you want to measure for your application, whatever other relevant metric, and again, collect it centrally. In this case, I'm just showing you the utilization. About 7% utilization improvement. Again, millions of dollars in savings every single year. It's not just the fact that we use less power to power these machines. We have to buy less machines. It means less silicon needs to be manufactured, less waste along the way of building it, less concrete. It's really impactful at our scale to the world. But beyond that, what we saw with Java 17 is the cold start, or starting up a new server, became a lot faster. And as a result, our failure rate of trying to insert new hosts into service, into the load balancer, improved by 98%. So this used to be the biggest problem for the service team. And just by upgrading from 8 to 17, a problem that was really bugging them for years just disappeared. And then at the end, it's always nice that the put latency, or writing a new metric, at the tail, at the P99, went down by 19%, right? So the overall effort here was a couple of weeks of work to upgrade from Java 8 to 17. There are some dependencies that got in the way, and we'll talk about that later. But the impact was tremendous. To get a similar impact, they will have to spend many months of work for multiple engineers from performance projects, which they should do as well, but this is the easiest low-hanging fruit they can use to get performance. So here's another one. This is a proxy service. A proxy service is something very common in AWS. So we have the backend that does the heavy processing, save your data, but there has to be something in the front end that takes the request from the user, authenticates it, routes it to the right backend server. This is a very common type of system we have in Amazon. In this case, the service was able to reduce the latency by 75%. If the tail latency for this service was up to 100 milliseconds, which means every request to the service or what's behind it can take up to 100 milliseconds. After this, the latency was, the typical tail latency was about 10 milliseconds up to 20 milliseconds. So really nice win for our customers. But along the way, this team was able to take on additional 30 to 40% more traffic. In this case, they chose not to descale the fleet because they knew end of year is coming. They were expecting 30 to 40% more traffic coming in, and they didn't have to do anything. They just didn't have to buy a new machine. They didn't have to pay rent to EC2 to get more machines. They just were able to absorb all that growth without extra spend, which is really nice. In this example, this is an analytics service. We're lucky here. And what happened here is this service did the upgrade from, in this case, from 11 to 17. So it's not just Java 8 is very old and been around for a long time, and Java 17 is just 2 years old. This is from Java 11, just 4 years old. What happened is they upgraded, but they didn't finish the upgrade. So we have the concept of availability zones. These are two parallel data centers that run basically with the same input. And unexpected traffic spikes came in. So a lot more load than expected for these systems show up. And in one availability zone, they're running on Java 11. And then the other availability zone, they're running on Java 17. So we got an unexpected A/B test, which is really cool. And what you can see here with the green line shows Java 11. You can see how the P100 GC time just spikes, the CPU spikes, and the latency goes through the roof, about 6 times worse, right? But what's more interesting about this is when we finished the upgrade, the team said, it's kind of cool, but kind of waste of time, because that's what you see. You see that section in the graph shows you, yeah, Java 17 is slightly better than Java 11, but really, this is such a low load system that it doesn't matter. It doesn't make any difference. And the thing I want you to take home from here is when you do these upgrades, you always have to think about load tests. You always have to think about the worst day. And the main thing we see with new versions of Java, yes, they're better all the time, or most of the time, but they really shine at the tail, and they really shine in bad days. And that is how you're supposed to scale your system, right? You scale them to the worst day of the year. You don't scale them to, midnight at your local time zone. You scale them to, if you're selling pizza, the night before the big game. If you're Amazon, we scale it to Black Friday, or at least scale it up right before Black Friday. And this is where the big wins come in. And the last one actually is a no improvement situation, which was also very interesting. So this is another proxy service, and it was running on Java 11. And one of the things this team has thought, this service is running on a GC called Shenandoah, originally developed by Red Hat and recently owned by our team, where we continue to develop it into a generational collector. And this particular team thought the main limit to their latency comes from Shenandoah not being able to give them the lowest possible latency. And Shenandoah had really nice improvements from 11 to 17, and the team was under the impression they're going to get great wins. The reality was, when they were done, they got nothing. They had exactly the same latency from when they started. So why am I celebrating it? So let's look at this graph. It's kind of hard to see at this point, but between August 24 this year to August 26, you can see how the GC pause duration looks a little bit better. It's kind of hard to see, so I'm going to zoom in for you. We can see it a little bit better now. What you can see on these graphs is 4 different metrics, the P50, or think about it as the average, latency, P90, 99, and 99.9. So the top one, the light blue graph, is 1 in every 1,000 requests will exhibit this latency. Let me zoom in again, just so it's easier to talk about. What you can see here is in Java 17, The P50 latency is no longer measurable. It's below the 1 millisecond resolution of this metric. So is the P90, right? The only time when you start to see interesting latency is P99, and P99 goes up to about 2 milliseconds, and P99.9 will jump up sometimes a little bit above 20 milliseconds. The reality, though, is there was no change because it turns out the rest of the latency comes from downstream calls, from code inefficiencies, and really that concept that Java and Java GC is a limit to low latency system is no longer correct, at least in this case. Right now, we're not resting. We're going to keep investing in Shenandoah, and Oracle keeps investing in ZGC, and there's continuous investments going on into Java 21 and 22 and so on. But it just shows you how important it is to get these upgrades and get them out. So if we're done here and the talk was done, this is what I want you to take home. Like, don't let anybody continue run Java 8. It's just done. The same with Java 11. I keep hearing people once in a while say, we're running on Java 8, so we're going to upgrade to Java 11, and we're going to do it step by step, and then we're going to go to Java 17. Forget about it. Don't waste your time. If you're on Java 8, you want to go to Java 17. I'm going to talk a little bit later about 21. And that's where you want to go. There are a few very special cases where you might want to stick on Java 11 and not go to 17. Like you might be stuck with CMS and you have to get off it and it's hard. I get it. You're going to be unique. You're going to be one of very, very, very few teams that I've seen really stuck on Java 11 for a reason. So is it all great? It's not. Let's talk about the bad. And really, it's not that bad. But you need to know about it, and you don't want to be surprised. I don't want to tell you a story where it's just great, it's just going to work. That's not the case. So the first thing to remember is, especially if you came from Java 8, there's a lot of APIs that are no longer open. You have to do add opens or export, or you might be depending on internal implementations that have changed. And we actually had a regression, a pretty serious regression in one of these services. We upgraded to Java 17. That particular service was using JSON. And inside JSON, there's a catch-all around serialization of objects, and in specifically a very specific object type wouldn't serialize anymore. But there was a catch-all. So we were running for a little while without knowing that we're actually not serializing the object, and it took us a while to figure out that there's a real problem. So what should you do here? A, you should be ready and know that this could happen, and the jump, especially from 8 to 17, is a big deal. Update your dependencies to the latest. Test your application. In this case, there was just a missing test for this type of input. And I know it's easy to say test all of it, but you really need to crank up your testing ability. Specifically, flaky tests, sometimes the test might not pass, and you're like, yeah, it's okay, this one doesn't work once in a while, and we'll get away with it. You're not getting away with it anymore. Flaky tests are one of the biggest limitations to doing upgrades. So put it on your list to get rid of. But the biggest learning from this case was that I actually didn't know about until after we were done with this. The JVM team at Oracle did us a big favor, and they actually write the error out. So if we were scanning std out and std error for surprises, they're going to be there. So whatever system you use that collects std out and std error, go and scan and look at the logs even after you put in production and see what's happening. Don't just store the logs somewhere and look at them at the day you have trouble. Look at them when you're done with your migration, and for a while. This could be that this type of object shows up once a day. You won't see it in your early tests. You won't see it in your pre-production. You might see it only when you get to production. Still worth the effort. And then the last thing is a gradual rollout. These upgrades are big. They're significant. Think about how you can just release it to a small part of your customers. Maybe the ones that are not hugely impacted by the error. And then after you get confidence, roll it out further. Here's another one. This is actually a very different case. In this case, we have a big AWS service that depends on parallel GC. Parallel GC is great when you have low amount of memory and you want to have high throughput. And parallel GC in Java 17 did a great thing. It parallelized the reference processing. What it means in plain English is your full GC pauses are a lot shorter because it just takes the spare CPU and compacts the process in parallel. However, in this service, what we saw, and you can see on the left side of the graph, Java 11, in the middle, deploying Java 17, and on the right side, the fix. What you can see is the CPU started spiking. And this service is defensive, and it says, I know when the CPU is going to spike, my system may get into a congestive failure state. So it starts on its own rejecting requests earlier before we get in trouble, and this way it protects the rest of the customers from a complete outage. And we couldn't understand what's going on because everything was better, right? And it turns out that there are multiple JVMs running on that machine, and when you get in that state, you can actually exceed your CPU quota and then get into the situation. The solution was quite simple. Set the parallel GC threads to a lower number. We still get a very nice improvement over what happened before Java 17 came out, and we no longer rejected customer requests and produced 500 errors that we didn't want to. So these are just two examples. There's plenty of examples like that. The point is that no change, as good as it could be, is just safe. Every change is a breaking change, and you have to pay attention, especially on these big upgrades. And here comes the ugly part. Again, not too ugly, and that's where we come in. That's where we spend a lot of time. Java 17 still has a lot of bugs. Java in general has a lot of bugs. It's just part of the nature of building something this big and this complex. These two specific bugs that I'm showing, I have a bunch more examples that are even more egregious, are things that we discovered only in the last couple of months and fixed. And of course, contributed upstream and backported Java 17, and all of you are going to get the benefit no matter what distribution you use. But the point is, when you do a major version upgrade like this, your application is a snowflake, and you're going to find things that nobody else has seen before. You just got to pay attention. So in this case, we found a case. The first bug was introduced early in Java 12, but slowly became worse and worse. And the only time where it became a big deal was in Java 17. And what it did, it created a memory leak during monitors deflation and inflation, and the application here just ran out of memory when it went to Java 17. And every time you do that, or at least when we do that, when we have tens of thousands of customers, we tell the customer 17 is going to be great, but if it's not, call us, and we'll be there to help you. And customers are still very disappointed. And if you get into a lot of these situations, they just stop the migration, right? What I want to tell you is this may happen. It's fine. Take the time, report the bug. We, Oracle, Red Hat, everybody else that's in the community is jumping on these and fixing them. This is why we care so much about update releases. This is the time to take something that is now 2 years out, right? It's been used massively. If you look at industry reports, we talk about 30, 40% of the workloads on 17 now. But there's still these significant bugs, right? There's more subtle bugs like the symbol table leaks. This is an interaction with Groovy 4 and the JVM triggering a new bug that we've never seen before. Again, the bug was introduced in Java 12, but because the feature releases don't get much adoption, don't get much care, it was just dormant until Java 17 and Groovy all came together. And again, this particular one we fixed. There's many others that other teams are fixing and taking care of. So what do you want to take from here? Just pay attention. You're not getting a perfect system, and it's not always your bug. And the question is Java 21. So what do we think about Java 21, right? Can somebody guess, help me guess, how many bugs are slated to be fixed in Java 21.01, which is coming out in October, right? Anybody want to care to make a guess? These are not bad guesses. So there's about 270 bugs. It's really hard to decide, so don't hold me to it. But these are numbers we looked at. So we looked at the bug database. We looked at it yesterday just to have fresh data. We think there are 23 pretty critical bugs in Java 21 that are already fixed in Java 21.01, and about 104 that are important but not egregious. And I'll tell you in a second what do I mean by egregious. And then similarly, 68 bugs for 12.02 already fixed.
21 or 12?
Sorry, yeah, my mistake. 21.01. Sorry, thank you. The bugs I'm talking about are memory corruption bugs. That level of, my byte buffer is going to have zeros in the middle instead of the data it actually should have, right? So for us, at the kind of systems we build, at the kind of trust we need from our customers, we're not ready to put 21 into production. We're testing with it. The results are amazing. We're super excited about Java 21. The throughput, the latency, it's exciting. But do we put Java 21 in production today? No. I just got off a call with a customer who took Corretto 21, put it in production, and called me and said, "What are you doing? We're trying to get a heap dump, and the process crashes. And it's part of our basic process to evaluate what's going on, and we build critical systems. We have to roll back." I'm like, "Well, you should have come to my talk. I'm going to tell you not to use it yet, right? Try it." So my recommendation to all of you, Java 21 is super exciting. Try it out now. Provide feedback. The sooner you provide feedback, the faster we can find all these egregious bugs and fix them. But I don't feel very comfortable putting in any of our systems in production just yet. I think it will also stand for us the same in January, and I think we're going to wait until April before we're going to go wide. If you just look at the numbers today, they're just a little bit too high for us to feel comfortable. But again, 2 years from now, it's not going to go to zero. Bugs are going to still pop up. They're just going to be a lot rarer, and you still have to ramp up your tests to be confident. So trying to wrap this up, here's a simplified migration guide. 217, which is where we recommend. You have to update your dependencies, particularly test frameworks like Mockito and PowerMock, Lombok, Juice, all these things use internal APIs. You just got to move them to the latest, and that's pretty expensive, but sorry, you picked them, you got to upgrade. Be very careful with strong encapsulation. A lot of stuff that was public, a lot of stuff that was unsafe is gone. It's good. It's good for all of us, but you need to get used to not using it. You need to look at dependencies that don't use it. And then the last thing we talked about, GC. GC is different. If you're on Java 8, parallel GC is the default. Now G1 is the default. Things behave differently. Even if you just upgraded and you're on G1, just start tuning it again. It just behaves differently enough, and it behaves so much better that often we just say, just wipe out all your tuning, start again from scratch, and often you don't need to tune anymore. The least Java flags you have, the better. CMS is gone. That's sad. It did a really good job for a subset of the applications, but we're finding that G1 mostly is able to replace it with some tuning. And you have new collectors. You have Shenandoah, you have ZGC and generational ZGC, and if you're looking for Lowe's Pulse app, these are really great collectors. For us, though, it gets really complex because we have a lot of stuff. We have lots of developers. We have many tens of thousands of developers in Amazon. We have many tens of thousands of services and hundreds of thousands of libraries. And we have this massive tree graph of all of them coming together. It makes our life hard. It makes it easier for you, though, typically, because you'll be in a smaller environment. It's just, but still something to think about. Your dependencies, both open source or third party as we call them, and internal packages, you'll need to move all of them off these problems we discussed before to be able to move to Java 21 or 17. So last, how do you future-proof? And I want to be a little bit controversial. First thing is use less dependencies in your code. It's very easy to pick a dependency to get stuff done. But we did a study with one of our applications. It had overall about 2,000 dependencies, indirect, of course. We cut them out. We started again from scratch. We deleted stuff that was small. We ended up with 30. Order of magnitude improvement, or 2 orders of magnitude improvement in life is a lot better for this particular application. There's a lot of unsupported dependencies that just been abandoned. That's just, there's one developer working on them and they move to work on something else. Just get rid of them. You have good tools to scan libraries. Really prefer ones that use publicly supported APIs. Of course, there's a few low-level libraries that do this stuff. You have to trust their developers. You have to trust their cadence. But if you can, really try to avoid mocks. I think your code will be better for it, and your life in upgrading will be better for it. Of course, it's your choice, right? Some people really swear by mocking, and I'm not here to start a war, but we find that mocks and things like Lombok are the biggest inhibitors for upgrades. So, and new features of Java, right? Just improve it altogether. We have records. We have a lot of new cool stuff coming in Java, or if you use Kotlin, a lot of the stuff that these libraries provide is already built into the language. The more you move to be off these crutches, the faster you can upgrade and get these benefits. Of course, testing. Test is a kind of double-edged sword. The more tests you write, especially if you mock, the more tests you have to upgrade. Still, the more testing you write, the more reliability you have in your ability to assess the upgrades. I've seen a lot of teams that say integration tests are not as important. We can do less of them. We cover everything in unit tests. That's all right. As long as you run your unit tests with the same JVM you're running your production, you're okay. But it turns out that a lot of people still test the library in Java 8 and then deploy it in Java 17, and then they're surprised as things don't work. So integration tests come to the help here in these cases. Invest in load tests. If you haven't done load tests really reveal the wins in the upgrade. Sometimes you have to sell the win to your manager, right, or to finance. Why are you doing this? Why is it so valuable? I see the same graphs, right? And you explain that this is how we save money. This is how we can, buy less EC2 instances or run less pods to get the same result, right? And don't forget your flaky tests. So metrics, always observe your metrics, especially after an upgrade. You've seen all these examples where we just see things from simple metrics. You can just tell what is going wrong without even having to deep dive. Fix anomalies in them. Don't accept that something has changed and you don't understand it. Don't chalk it up to, it's fine. It turns out that every time these things happen, they're not fine. There's surprises waiting for you on the worst day of the year. Do it when you have free time, when you're not stressed out, when it's not Black Friday. We talked about log analytics, and of course, modern DevOps practices really help with that, or really help us. Running through a pipeline, having a beta stage, having a fractional deployment, having an automatic rollback, having production canaries, in 99% of the cases, just prevent that problem from being inflicted on the customer. The service team will find out about it and roll back before any harm is done. The more you have these practices in place, the easier it is for you to have an upgrade done. And kind of to recap this section, and I want to invite James to take his, don't leave broken windows behind. Minimize the things you don't understand about operating your app, and your upgrades will become a lot less scary. You'll save a lot of time to the company, and remember, a lot less CO2, a lot less power, and do the world some good.
All right. Thanks, Yishai. So I'm going to have to talk really fast because I'm down to 10 minutes here. So I'm going to talk about the IoT side of the world and some lessons that we've been learning running customers that do IoT stuff at scale. And most of it's good. Some of it's bad. Some of it's downright ugly. The good stuff, of course, one build, one binary, that actually works. And especially on the Amazon side, where our stuff has to run on a wide variety of chipsets. We do one build of most of our IoT stuff that's going to run on IoT devices. It really helps with reliability, and a lot of the reliability stuff in Java was originally motivated by building reliability. Many people, there are things that were about reliability that people don't really think of as being about reliability. So like the tight memory model, the exception handling system, the fact that you can catch anything. I tend to think of the Java exception model as something that lets you make a really, really tight scale blast radius. And particularly in the IoT world where you can't just like fail and let the next guy take over your load because you're the only one on that box that's nailed up to the side of a building somewhere. But so that's kind of the generic stuff. Oh, and developer velocity, and all the issues around testability. It is so much easier to test Java code than it is to test C code, and the bugs tend to be easier to find than just kind of like generic memory corruption bugs. And people don't think about that very much in the cloud world because the amount of C code is relatively small. But in the IoT world, everybody is used to using C, occasionally C++, and these crazy test schedules are in there, and they just live with it because they're electrical engineers and they believe that pain is life. And so they get a whole lot of velocity back once they realize that there's all these tools for doing testing. And one of the things that Yishai mentioned was that we get these exotic bugs in the Amazon cloud that will, across, a million processors running 24 hours a day, a bug will show up like once a day. And, you can do all kinds of testing, but that no matter how hard you test, things are going to leak out into the real world, and you're going to have to be able to handle them. And so, all of the tools that are available for doing testing, monitoring, management, probing VMs that are running in the wild, to be able to do sort of harvesting of fault data live. Because it's always in the live production systems that the nastiest bugs show up. And that has helped people a lot. And another really nice thing has been performance. If you look at the performance over the generations, it's wonderful. Just, basic code performance has been really, really good. People have been doing like bake-offs between using LLVM and using Hotspot, and they're essentially indistinguishable. And actually, there are reasons that fairly often Hotspot actually wins. But the biggest thing is the GC. Not only are all the throughput numbers that you saw in Yishai's talk just really, really there, but if you're reasonably careful, you can get GC pause times that are capped. And so we start seeing people using Java in places that would normally be hard real time. And of course, the other really good thing is so many libraries. There's libraries for absolutely everything, especially when it comes to being an IoT device in a networked world. So what's bad? So many libraries, right? Basically, a strength is also, turns out to be in many ways a weakness, and in many different ways. So one of them is that a whole lot of libraries have embedded C code. Sometimes for just lame reasons, but often for fairly good reasons. You find things like the Amazon crypto library or the Matter smart home library, where it's really important to not re-implement things because the standard, while it is written down as a standards documents are really, as much as they say they capture the truth is usually in the code. And so for things like the crypto library, it's like one implementation across all languages. And same thing with like the Matter smart home library. It's like the canonical one that's on GitHub. It's written in C, just use it. But life gets a lot easier because the gateways into that and the packaging facilities have gotten really pretty nice. Most people in this room don't care about memory footprint because you're mostly cloud developers and you've got gigabytes, if not terabytes, to just sort of burn away. And yet tools like JLink help a lot. JLink is definitely your friend. You can, if you're really brave, you can do custom JVM builds to set conditionals and carve things out. And you can also do like per platform packaging, or you often have to, but at least in this universe, most customers only have one CPU platform that they care about. But the really ugly stuff is about size. The memory footprint can be large. When people do audits, and I've been involved in several audits, it's not the JVM that's the problem. It's the libraries. It's pretty much always the libraries. And there's kind of an embarrassment of riches. There are so many ways of doing the same thing. And if you call, this library here, it might call that library there, but that library there, they decided that they needed to have their own implementation of HTTP. And I mean, if you ever do one of these memory audits, one of these code-loaded audits, it's pretty common to find like 4 copies of HTTP loaded, right? There's the Apache Commons HTTP library that is commonly loaded. There's in the AWS SDK, under the covers, you can't access it, but it's there. There's another HTTP library. If you use many of the Google libraries, they have their own HTTP implementation. And then there's the one that comes with the Java platform, which a lot of stuff uses. And then you find that kind of pattern repeats with things like Netty, right? There are people who fork Netty. And it's because they disagreed with one API. So that's got to be fixed. And how many serializers? It's pretty common to go through an app and find like a bunch of different JSON serializers. And in the world of essentially infinite memory, not a big deal. Enjoy, But when you have to worry about space, it turns into really ugly. And it becomes especially ugly because all of these libraries, you think you're calling like one routine out of library A, but that one routine, maybe, 99% of the time, it just does its thing. But then it's got an exception case where it calls that routine, and that routine initializes a table, and that table initialization says, okay, let's download this thing from the web because we need this table of such and such, whether it's currency exchange rates or time zone definitions. And now you've pulled in all of the HTTP library, and all I wanted was this one little routine, And back in the day when the transition from JDK 8 to JDK 9, all the modularity stuff, one of the biggest sources of pain was trying to cut down on the sort of death by transitive closure. And one of the really ugly parts of this is kind of a social thing in the engineering crowd, right? That they, because all this open source stuff is out there, there's some library you like, you're using it, some routine doesn't work. It's either a bug or a misfeature, right? So you clone the library, you make the fix, now you're deploying that library with your app. That's fine, except that now there's probably 2 copies of that library because you've done this and then somebody else has done the same thing or is just using the stock one because it's fine. And a lot of the times, these changes are things that, to a first approximation, you should just file a bug report. And there are so many bugs that get fixed without filing a bug report on the project maintainer sites. And then if you're really feeling like a community member, which you really, really should, is, if you're going to fix the bug for yourself, fix it for everybody else. Submit a pull request. And I know that most engineers hate getting involved in social things because humans are scary. And, the audience in this room is sort of self-selected to be the people who are better off at the social side of things because, there's lots of people here. But, get over it, right? Pull requests are so much more powerful than fork. Just do it. And I personally have this thing that I try to never ever download the source of any library I'm using unless it's truly a problem. And that's one of the things that I find is interesting as a distinguishing thing between the Java community and just about everywhere else, because it makes sense to download binaries and just use them. It's not like in the C world where you pretty much have to download the source and recompile them, unless they're the sort of thing that's, libc.so equivalent. And, the kind of things that's already way ahead of you in like the Debian release or something like that. You end up having to copy the sources, and then you've got the maintenance problem and the fact that you've got to do bringovers and then redo the tests and yada yada. You've all been there. But the situation is actually mostly good. The painful bit is size. On anything bigger than like a Raspberry Pi 2, like Raspberry Pi 3 or 4 or 5, or any systems that are kind of comparable to that, and that includes essentially every industrial automation system you've ever seen, if any of you have ever seen one. it's all good. If you're trying to do things on like a Pi Zero, I mean, I know people who've made Java work on Pi Zeros. It's an act of heroism, but there's sadness involved. But you know, it's largely a good thing. So, thanks. We have negative time now. I don't know who's controlling the clock. Should we do some Q&A or just call it we're just done? We're just done. Thank you. Oh, and we'll be down in the Amazon booth right after this.